welcome everyone to the lecture series of our course Marketing Research and Analysis. So, we were continuing with hypothesis testing in different cases, right. So, for example, we in the last class we covered hypothesis testing of means when population standard deviation is known, right. So, but as I said, it is a very rare case, you are not aware of the population standard deviation most of the time. So, that is a very generally not applicable. Hypothesis testing using the standardized scale, right. Second, one tail test of means and hypothesis testing of proportions. So, we dealt with these cases in the last lecture, right. Today we are going into the we will move ahead with different other cases and how does a researcher handle them, right. So, these are very important, I have been repeating all the time. Kindly have patience, whenever you feel like you are not understanding, take a pause, stop it and try to go back and see whether you are understanding it or not, right. Once you are clear, then only you should move ahead. Okay. So, the next case we are going to deal with it today is the hypothesis testing of proportions in case of large samples. Okay. So, we are talking this time about a one tail test of proportions, right. So, let us start the question. A member of a public interest group concerned with environmental pollution asserts, today nowadays people are talking about environmental problem and how it affects us and all. So, one of the PI public interest group they assert that fewer than 60% of the industrial plants, less than 60% of the industrial plants in a particular area are actually complying with the air pollution standards. So, they are worried that people are not complying to the air pollution standards, less than 60% are actually following it. Attending this meeting is an official of the Environmental Protection Agency from the government maybe, who believes that 60% of the plants are complying with the standards, right. It is not 60%, less than 60%, but this person from the Environmental Protection Agency, they believe that it is 60%. She decides to test the hypothesis at 2% level of significance. How much? 2% level. The official makes a thorough search of the records in her office. She samples 60 plants. How many? 60 plants from a population of over 10,000 plants and finds that 33 are only complying with air pollution standards. This 33 is out of 60. Okay. Is this assertion by the member of the public interest group who said it is less than 60%, is it a valid one? So, now the researcher is facing a problem where he has to check whether the statement of the public interest group person, whatever he has said that is less than 60%, is it true or not true, right. So, first kindly frame the null and the alternate hypothesis in this case. So, what is of interest to you and what is the null hypothesis, right. So, kindly write it on your notebook or something if you are following the class listening to me. So, what is it saying? P is less than 0.6. The environmental agency is interested to see is it really less than 60%. Okay. So, that is they are trying to check. So, what is the null? The null is equal to 0.6, fine. Alpha is 2% level of significance. So, our hypothesized proportion is 0.6. So, the Q or the rate of failure you can say is 0.4, N is 60. So, now the sample that they took was 33 in which it was 60, out of which 33 were found to be actually having a problem. 33 are complying with the air pollution standards, that means they were good, 33 were good. So, what is the the good one? 0.55, 33 by 60. So, what is the ratio or the proportion of the group which are not following the standards? Now, Q which is equal to 0.45, right. Now, since NP and NQ are over 5, right, we can use the normal approximation of the binomial distribution. In this case again you see we have taken 0.48 of the area under the curve. Why? The reason is, again let us go back and think, we are talking about only one tail. So, the less than, we are interested in the less than case, right. So, in this side, that means we are not interested in this side, right. this is of no interest to us, we are only interested in this side. So, 2% is the level of significance. So, the 2% is the rejection part. So, out of 2 when you minus 50, that means it is the area is 0.48, right. So, for that the critical value of z for 0.48 of the area under the curve is how much? 2.05. Okay. Now, first you will calculate the, as you remember, the standard error of proportion. The standard error of proportion is root over of p q by n. So, by using this formula we have calculated that in this case 0.0632. So, using this standard error of proportion, let us calculate the z value. The z value is proportion of the sample minus hypothesized proportion upon the standard error of the proportion, which is giving us a value of minus 0.79. Okay. So, minus 0.79, the standardized sample proportion, that means falls inside the region of acceptance. Now, correct, you see minus acceptable the limit was minus 2.05, let us say, and our case is minus 0.79. So, that is much within the acceptance region. So, the calculated value is minus 0.7 and the critical value is minus 2.05. So, the sample proportion lies within the acceptance region, right. EPO officials, now this part is very important from a researcher point of view, this is what you need to write. So, the EPO officials should accept the null hypothesis that the true proportion of complying plants is 0.6 or 60%, right. Although the observed sample proportion is below 0.6, it is not significantly below 0.6 to make us to accept the assertion by the member of the public interest group. That means what it says, you are accepting the null hypothesis. So, what was the null hypothesis? That proportion of the plants complying with the standards is not less than the 60%, but it is 60%, right. Now, coming to the next case. The next case is hypothesis testing when the population standard deviation is not known to you, right. This is of means now, this case is again of means. Earlier we were doing with means, then proportion, now again coming to means. So, this is a two-tailed test of mean in which we are using, let us see what is the case first. A personal specialist of a major corporation, a personal human resource person, officer of a corporation is recruiting a large number of employees for an overseas assignment. During the testing process, management asks how things are going and she replies, fine, I think the average score on the aptitude will be around 90, the average score of the sample, right. When management reviews not sample, this is the hypothesized mean, right. So, when the management reviews 20 of the test results, this is n is equal to 20, it finds that the mean score is actually 84. So, this is the sample mean, right, and the standard deviation of the score is 11. So, your hypothesized mean is 90, n is equal to 20, sample mean is 84 and sample standard deviation is 11. Okay. So, this is a case where the population standard deviation is not known and you see the sample size is less than 30. So, this follows a t distribution, right. If management wants to test her hypothesis at 10% level of significance, how should they go ahead? Again I would say take a break and frame the null and the alternate hypothesis first. Okay. So, what is the researcher interested here? They are interested to see whether the mean score is 84, right, and whether the hypothesis is correct or not. So, what was the hypothesis? The hypothesis was that the average score will be around 90. Okay. So, mu is equal to 90, but what is the researcher's interest? No, mu is not equal to 90. So, this is what is of interest and automatically mu is equal to 90, this is our null hypothesis. Because management is interested in knowing whether the true mean score is larger or smaller than the hypothesized score, obviously a two-tailed test is appropriate. So, sample size is 90. Now, this is important. I think I have explained already what is the degree of freedom, right. This degree of freedom is of critical importance, especially in the case of a t distribution, because when you look at the t distribution, the value, the area under the curve, when you want to calculate, check it, this degree of freedom is of vital importance to you. So, this degree of freedom is nothing but all the time the n minus 1, right. So, that means since the sample size is 20 and maximum it could go up to 30, the degree of freedom in this case is 19, 20 minus 1. Okay. From the table, the critical value of t for that means for 19 degrees of freedom, right, at 10% level of significance is equal to 1.729 as said, right. Now, let us calculate the standard deviation. So, the standard error. We know that the standard deviation in this case we have to use it for the sample because the population standard deviation is not known to us. So, let us use the sample standard deviation which is given to us as 11. So, from here the estimated standard error, this sign is estimated, right, is equal to estimated standard deviation which is the sample standard deviation divided by root over of n. So, that means this is equal to 2.46. Now, using this we will calculate the t value, t or the z value. This is the same formula, right, z or t is equal to x minus mu upon standard error. So, this is coming minus 2.44. The critical value of t is, we have seen how much now, 1.729, the t value from the table. So, now please interpret, how does it look? Now, it is something like your acceptable limit is minus okay, minus or plus whatever 1.729 minus and plus 1.729, right. What is your calculated value? Now, minus 2.44, right. So, minus 2.44 is beyond this limit, right. So, the null sample mean falls outside the acceptance region. So, this is the acceptance region, right. Therefore, management should reject the null hypothesis. The personal specialist's assertion that the true mean score of the employees being tested is 90 is therefore rejected, right. I think this is clear. Okay. Let us go to the next case, right. Now, we will test for differences between means of large sample sizes again. This is for large sample sizes, again similar case, but there are two samples here, right. This is a case where a manpower development, earlier you were dealing with one sample only, is asked to determine whether the hourly wages of workers, whether it is the same in two cities or not. See, this is many a times you also face in life that I want to know whether the HRA given in two cities that may help you in deciding whether you should change your location or not, because the company is giving same HRA or different HRA, and how much is that, is it significantly different or not. So, such things help you to decide, right. The result is given to you. So, there are two cities are Apex and Eden, right, and the mean hourly earnings from the sample are $8.95, $9.1, right. Standard deviation is also given to you, the size of the sample is given to you. Now, earlier you were dealing with only one sample, right. Now, how would you proceed here in this case? What should you do? Just think for a while, how would you approach this problem? There are two samples and you want to, this is a case of a, in simple terms we say independent sample test, right. So, first you will again write the null and the alternate hypothesis. So, what is the null and the alternate? The alternate is there is a difference obviously, null is there is no difference. Let us see. So, mu 1 is equal to mu 2, no difference is my null hypothesis. Mu 1 is not equal to mu 2 is my alternate hypothesis, right. But since I am not telling who is which one is bigger, so I do not know exactly which is the direction of the test, right. So, therefore, it is a two-tailed test. But had I said ki the mean of let us say Apex is more than Eden, but how much it is not sure, then in that case maybe I would have gone for a one-tailed test. Okay. Both samples are large. Why? The sample size was how much? Let us see, 200 and 175, so more than 30. So, we use the normal distribution. So, the area under the curve is how much? 95% divided by 2. So, 95.95 divided by 2 is equal to 0.475, right. This value is 1.96, time and again we have been doing this. The standard deviation of the two populations are not known to you, the standard deviation of the two populations are not known to you. Therefore, the formula for the estimated standard error of the difference between the two means we will assume we will take these two values, right, the sample standard deviations. When it is the population standard deviation is not known, we know that we will take the sample standard deviation and then calculate the standard error. The standard error of the difference between the two means now is something like this. Earlier what you were doing, sigma x is equal to sigma by root over of n, but here what we have done is we have just combined the values. So, now this case sigma x1 x2 right of the two samples is equal to root over of sigma 1 square by n1 plus sigma 2 square by n2. So, that is giving us a value of 0.053. From after this, the next step we all know by now is that we need to calculate the z. So, how will you calculate the z? Earlier the z was x minus mu upon standard error. So, now we are just replacing like this x by x1 minus x2, correct, minus again it is same mu 1 minus mu 2, correct, same, nothing has changed, divided by instead of sigma x we are having sigma x1 x2, correct. So, now if you see, this is interesting, what is your null hypothesis? Now, in this case mu 1 is equal to mu 2. So, if mu 1 is equal to mu 2, that means mu 1 minus mu 2 is nothing but 0. Okay. So, what remains is z is equal to x 1 bar minus x 2 bar upon the sigma x 1 x 2. So, this is equal to minus 2.83. So, what is saying? The standardized difference between the two sample means lies outside the acceptance region. Is it true? Let us see. Minus 2.83 is much further away from the acceptable value of 1.96. Okay, 1.96 we had, yes, right. So, therefore, the null hypothesis is rejected. We reject the null hypothesis of no difference and conclude that the population means differ in the two cities. As I said, example, you can think of house rent allowances, or the salaries between men and women, right, gender wise, several studies where you are trying to seek whether the two samples are they varying significantly or not, right. Now, we will go to the next case. This is a testing differences between means with dependent samples. That means, what is a dependent sample? One sample which has been tested once, again the same sample is tested again. So, the sample actually has not changed, the sample is same, but it behaves like two different samples, but actually the sample is same, right. As frequently I give the we say in case of medicine or something, we check the drug on a particular sample, give the medicine treatment, right, again you check the efficacy of the drug. Okay. So, a health spa has advertised a weight reducing program and has claimed that the average participant in the program loses more than 17 pounds. What is he claiming? He is claiming that the average participant in his program loses more than 17 pounds. A somewhat overweight executive is interested, right, but he is doubting the claims and asks for hard evidence. The spa allows him to take a record of 10 participants. So, n is equal to 10. So, if n is equal to 10, that means we understand it is a small sample. So, t distribution, and measures their weight before and after the program. So, 10 people, 10 participants before, then they participate in the program, exercise, and then after that they again measure their weights. These data are given. So, before what was the weight? So, this is the weights before 189, 202 goes on till 233. After the going through the program, the weight, this is the weight. Now, we have two samples that are clearly dependent on each other, right, because same 10 people have been observed. The overweight executive wants to test at 5% significance level whether the claimed average weight loss of more than 17 pounds is true or not, right. Take a pause again, frame the null and the alternate hypothesis. Okay. Let us see. So, what is he interested in? Now, the difference between the two is more than 17 pounds, correct, that is what was the claim. So, he wants to check whether this is true or not. Suppose it is not greater than 17, then the claim is false. But what is the other side? What is the null hypothesis? Now, mu 1 is equal to mu 1 minus mu 2 is equal to 17. He is not interested to look at the whether it is less or not. He is saying it should be greater than, the claim was there, it was greater than, right. Conceptually, we have not two samples of before and after weights, but rather one sample of weight loss. If the population of weight loss has a mean of mu 1, we can restate our hypothesis as this much, like mu 1 is equal to 17 and mu 1 is what do I mean by this saying this? That means what it means is the sample 1 whatever value, let us say x 1, x 2, x 3, sample 2, that means next time what the weight was x 4, x 5, x 6. So, this minus x 1 minus x 4 is equal to whatever, let us say x 1 1, let us say put it this way, x 2 1 is equal to x 3 1, suppose I am just getting. So, this difference is it like it is behaving like one sample. So, this difference is what is of concern to us. So, he says this difference mu 1 is equal to 17 in the null hypothesis, mu 1 is greater than 17 is the alternate hypothesis. The t distribution is used because the sample size is only 10 and the number of degrees of freedom is 10 minus 1, so 9. From table the critical value of t is 1.833. So, you need to check the t table. So, it is 1.833. Now, how do you calculate this? Individual losses, their mean and standard deviation will be calculated after, before, after. So, this is a loss. So, this is what I was just talking about in the previous slide, right. So, either you can, there are two ways you can do this. So, this is one, you calculate this loss squared and use this formula. So, what is the formula? So, what is that you see this you have calculated. So, sigma x square by n minus 1 minus n into x bar square by n minus 1. Using this formula you can calculate the sample standard deviation which is coming as 4.4. You can do it in the other way also, very simple way is S is equal to x minus x bar, right, x minus x bar square, right, x minus x bar square by n minus 1 root over. So, if you use the same formula, now what is this x in this case and what is the x bar? So, the x bar is nothing but the mean of this, okay. So, 19 plus 23 plus 17 plus 15 plus 22 plus 16 plus 19 up to 29. So, the mean divided by 10, right. So, that is the x bar. So, this is the x bar. So, we have calculated. So, x minus x bar all the time. So, 19 minus the x bar, 23 minus x bar. So, you find out this and square, correct. So, using this you will find the same value, almost the same value, right. So, this is the summation you have taken, this after doing this is the summation you have taken and you have calculated. The standard error of mean now has been calculated to be 4.4, which you calculate through this way, right. Sigma x is equal to 197, x bar is 19.7, sigma x square, right, this value, right, is 4055. Taking this we calculate the S, the standard deviation, which is equal to, formula is root over of sigma summation of x square divided by n minus 1 minus n x bar square divided by n minus 1. Or you can simply, what you can do is, I would just you can use this formula, I had already used it. So, this formula is nothing but summation of x minus x bar square divided by n minus 1, right. So, this root over when you take, you calculate the sample standard deviation, which is the same value you will get, okay. So, x is given to you, x bar is just you have to take the summation of this and the mean, right. So, I think we have calculated here x bar. So, now the question is, once you have calculated, then you find out the standard error of the mean. So, which is coming to be 4.4 divided by 3.16, 3.16 because n is equal to 10. So, 1.39. So, now if it is 1.39, so let us calculate the t value. Now, the t value says x bar, which is x bar minus mu upon standard x. Now, x bar was how much? X bar was 19.7 minus mu, now mu was 17, right, divided by standard error. So, that is equal to 1.39. So, when you divide, the value is 1.394, but your critical value is 1.833. So, if it is 1.833 and this is 1.94, that means the value is actually going beyond the critical value, right. So, it is lying somewhere outside the critical value. So, since it is lying outside the critical value, the executive can reject the null hypothesis and conclude that the claimed weight loss in the program is right, is true. That means, it is actually less greater than 17 pounds. Okay. So, this is the case of a dependent sample. So, almost all medical cases or all training type of things where a person is to be checked whether what happened after, something has been done, some training has been given or some medicine has been given, some surgery has been done. In such cases we use this dependent sample t test. Okay. Now, let us take a two-tailed test for differences between proportions now. So, you have talked about means, now again coming back to proportions, right. This is the I hope the second last problem we will be doing. A pharmaceutical manufacturing company is testing two compounds to reduce blood pressure. The compounds are administered to different sets of animals. In group 1, 71 of 100 animals tested responded to the first drug. So, that means P 1 is equal to 0.71. In group 2, 58 of the 90. So, that means P 2 is equal to 58 by 90. Okay. The company wants to test at 5% level of significance whether there is a difference between the efficacies of the two drugs. So, kindly again start writing your null and the alternate. So, P 1 is equal to 0.71, Q is equal to 1 minus P 1 that is equal to 0.29, N 1 is 100 in this case, P 2 is equal to 0.644 that means what 58 by 90. Okay. Is equal to 6 points. So, Q 2 is equal to 0.356, N 2 is 90. Our null hypothesis is that there is no difference, because the alternative which is of our interest is that there is a difference between the drugs, but we do not know which drug is more efficient, right, at the moment. Alpha is 5% level of significance. Both samples are having a large sample size to justify the normal distribution, right. From the table, the critical value of Z for 0.475 of the area under the curve is 0.96. Okay. From the table, the critical value of Z for 0.475 of the area under the curve is 1.96, that we have seen regularly from other problems. Now, how do you deal with this condition? So, the estimated overall proportion of success, because there are two populations here, right, two populations, correct. So, one responding to drug 1, the other one responding to drug 2. So, here you have to take a combined effect. So, how do you calculate the combined effect? The estimated proportion of success in the two populations is N1 P1 plus N2 P2 divided by N1 plus N2. When you do this division and combined, it generally normalizes the effect. Okay. So, the combined proportion of success is finally 0.6789. Okay. Similarly, estimated standard error between the difference between the two proportions is how much? The sigma P1 P2 is equal to PQ by N, which was the formula we had, plus PQ by N2. So, we had P1 Q1 by N1 plus P2 Q2 by N2. So, this is what is of interest. So, you can do this and you calculate. So, again it is coming 0.6789, although the value is the same as the proportion of success. It is a, because we are using these two values now, this value plus this value also to finally calculate our Z value. So, Z is how much? Now, P1 minus P2 minus the P1 minus P2 of the hypothesized proportion, right. This is the sample, this is the hypothesized. So, these two obviously you said P1 minus P2 is same, correct. Actually, you should this is the hypothesized proportion. So, you should be taking the hypothesized proportion. So, we said that these two are same. So, when these two are same, automatically the formula says P1 bar minus P2 bar. This is, please do not take it bar, this is just P1 minus P2, right, divided by sigma P1 P2. Okay. Okay. So, this is because this part is automatically 0, okay. They are equal. So, that is why the Z value is 0.973. The standardized difference between the two sample proportions lies within the acceptance region. Is it true? Yes, 0.973 lies within 1.96. So, we are accepting the null hypothesis or not rejecting the null hypothesis. We accept the null hypothesis and conclude that these two new compounds produce effects on blood pressure that are not significantly different, they are almost same. Okay. So, I hope you have understood till now. We will come to the last case now. So, one tailed test for differences between proportions, this is the last case for the day. Let us take this case. Now, here it is slightly different, because this is a case where for tax purpose a city government has been using two methods of listing property. The first requires the property owner to appear in person before a tax lister. You have to come in person, you have to visit the office. The second permits the property owner to mail in a tax form, you can email that. The city manager thinks the personal appearance method produces less mistakes than the mail, because obviously nobody is there to guide you. So, that makes more mistakes, the mail method. She authorizes 50 personal appearance listings and 75 mail listings, right. So, personal is 50, mail is 75. Okay. 10% of the personal appearance forms contains errors. How much? 10%. And 13.3% of the mail contains error. Okay. Now, the results of a sample, which can be summarized as P1 is equal to 10%, Q1 is 90%, right. So, P1 is our she is interested to check the mistakes. So, 90 and so success is actually the mistakes this time. Q1 is 90, N1 is 50 first case. Similarly, P2 is 13.3 or 0.133, Q2 with no mistakes is 0.867 and N2 is 75, the second sample. The manager wants to test at 15% level of significance whether the hypothesis that personal appearance method produces a lower proportion of errors, is it true or not. How should they proceed? So, again please pause, take a pause and write frame the null and the alternate. So, in this case what was she trying to see? Ki P1, which is P1 was your personal appearance, had lower mistakes than the mail, that is what they are interested. So, first write this one, this portion. So, this is a one tail test, correct, and if this is not true, what is the null hypothesis? Now, there is no difference. So, P1 equal to P2, right. With samples of this size, we the critical value of Z for 0.35 of the area, because 15% that to one side. So, one side is 0.5, the other side, the left side let us say is 0.35, okay, because 0.5 minus 0.015, because it is a one tail test, okay, is 1.04. The city manager wants to test this which one is good, right, which is there a difference or not. So, again let us calculate the proportion the proportion of success, right, overall proportion of success, and it is equal to N1 P1 plus N2 P2 divided by N1 plus N2. So, calculating this we get 0.12 overall proportion of success. Using this you calculate the standard error of proportion. So, again so this is P1 Q1 P2 Q2 by N2, right. So, please this is slight typological error, you can check this, right, and then you calculate, which comes to 0.0593. Similarly, you know this one is again finally 0, right. So, this is 0. So, coming to this we calculate the final value is minus 0.556. So, the standardized difference between two sample proportion lies well within the acceptance region, which was how much? What was the critical value? The critical value was 1.04. So, 1.04. So, therefore, the city manager should accept the null hypothesis and that there is no difference between the two methods of tax listing. At this moment you cannot say that there is the difference in the claim, that whether they appear personally or they appear they send it through the mail, there is no difference at the moment, we cannot make that claim, right. So, these are the different ways, the formats of testing a hypothesis when you have one sample or let us say two sample or the same sample getting repeated in a case of dependent sample test. So, moreover this is what we are testing, and I think you must be very clear at the moment, and some typological errors which were there, kindly correct them, you may correct it because you have understood it, and I hope it is clear to you, the objective, the formal, the things are very clear to you, and wish you all the luck. Thank you so much.